Format string exploitation. Today we'll be discussing format string exploitation. This type of vulnerability arises when a program takes user control input and uses it directly as the format string in functions like printf. Instead of printing text, an attacker can input format string specifiers, tricking the program into interpreting them. This opens the door to reading from and even writing to memory. Essentially, format string vulnerabilities can derive into arbitrary read and arbitrary write primitives. Specifiers like %d, %u, or %x read integers in different forms. %p reads pointers, and %s reads a string from a memory address. %c reads a single character, and %n writes the number of characters printed so far into a memory address. Later, we will see most of these format string specifiers in action. To gain precise control in our exploits, we use modifiers. Size modifiers allows us to dictate the size of the data being read or written. For example, %hn writes 2 bytes, while %lx reads an 8-byte long integer. We also have positional arguments using the $sign syntax, like %7$p. This is incredibly useful because it allows us to directly reference the 7th argument, skipping others. Although there are libc versions like musl that do not support this. Lastly, width and precision modifiers like %4c allows us to set the exact minimum number of characters to print. This will become essential when we start writing data, as we will see later. Let's see a small example of how to use printf as a developer. So, here we are defining some variables of different types, for instance an integer i1337, an unsigned long integer ul hex1337, then a string, and then this integer value. And we are using printf to print several values, for instance the I, the ul in several formats, the string, the first character of the string, the address of main, and then we are storing the length of this string into the variable n. So we have compiled the program, and if we run it, we will see exactly what we expected. So this is the 1337 in decimal format. Here we have the hex 1337 in decimal format and the 1337 in hex format with a padding of 4 zeros. So the hex string is 8 characters long. Then we have the string, the first character of the string, the address of main, and all of this is being written, the length of this string is written to n. So if we actually take this echo -n and this is exactly 87. So let's debug it with GDB to see how these values are stored in registers and on the stack. So let's press start and let's continue until we reach the printf right here. So notice we are about to call printf and take a look at the registers. So as you can see, the RDI register, which is the first argument, holds the format string itself. Then we have RSI, which is the value of 1337, but here it is in hex format. Then we have RDX and RCX, which hold the same variable, which is 1337 in hex here. Then we have the string, and as you can see, the string is represented as a pointer to a string. Then we have the first character of the string, which is 54 in hex, which is the ASCII value of the capital T. And then the remaining arguments are sent through the stack. So as you can see on the stack, we have main, and then we have the address of this variable n. So here at this point it is exactly 0 because this is an integer, so this is a 4-byte value, and now it is a 0, but after calling printf, this should be 87. So let's actually take this to monitor after that. Next instruction, as you can see, printf has printed this string, and at this point n has this value, which is exactly 87, and that's it. Hopefully it will be clearer when we start exploiting this format string box. The first step in a format string exploit is often leaking memory. By passing format specifiers like %p or positional ones like $7p, we can read values directly off the stack. This is fundamental for bypassing mitigations like ASLR and PI. By analyzing these leaked values, we can determine the base addresses of the ELF binary, the glibc library, the stack, or heap. We can even leak the value of the stack canaries to bypass this mitigation. Finding the right offset is as simple as proving positional indices iteratively. We can also leak values as a string, as we will see later. Let's have a look at this small challenge where we have a clear format string bug here. So, as you can see, this data buffer is filled with fgets. There's no buffer overflow here, but this data buffer is set as the first argument of printf. So, as an attacker, we can place format specifiers right here and leak memory and potentially write into memory. As you can see, GCC also warns that we have a format string bug here. Okay, let's take a look at this. Okay, this is hanging because it's expecting user input, and it just echoes back the user input using printf. So if we place, for instance, %lx, we will see a memory address or some value in hex. Instead of having %lx, we have this value. We can also do %d, for example, and we have, well, the same value but in negative form. And we can place %p, which is the same but with this 0 hex before. You can use again p and several times. And well, we can see several values separated by periods. And one thing to note is that we have 1, 2, 3, 4, 5, and 6. And notice that this sixth value is repeated several times. And let's see what's this value. This value is exactly %p dot %p dot %p. So, well, it's the format string, but in little endian format. So we know that the format string is stored on the stack, and as you can see, this is the 6th position. So we know that the format string goes into the first argument, so RDI, then this is RSI, RDX, RCX, R8, R9, and any more arguments are passed through the stack. So this is where we have control over the arguments of printf. So for example, if we use A, B, C, D, E, F, G, H, so 8 letters, and now we place $6p, we can see that this value should be written right here, and we are referencing the 6th position on the stack, well, the 6th argument, which is the first position on the stack, so this one. And we can also do the same using $7p. Now this is 4 bytes, so we need to pad it with 4 bytes more to adjust to 8 bytes. And now we can say A, B, C, D, E, F, G, H. And as you can see, we have again referenced this 7th position, which is the 2nd position on the stack. So this thing should be here, and this A to H should be here. So the 7th position is this one, and it's right here. So using this, we can reference other values, and this will be quite handy for writing into memory. Now, we can also leak other stuff, for instance, using percentage, I don't know, 30p, well, percentage 31p, percentage 40p. Well, there are memory addresses in the stack, so we can find a lot of addresses, but instead of writing this manually, we can do a for loop and iterate over from 1 to 100, for example, and see what kind of addresses we have. So we can find binary addresses, the stack canary, glibc addresses, stack addresses, and we should find the correct position in order to develop the exploit.